Welcome to WhatsApp with Power, where we explore concepts worth understanding. In this video, we are going to explore an important concept in power system protection. Why does a current transformer, or CT, saturate? We will understand the physics behind it and explain what's actually happening inside the CT. To understand CT saturation, it's important first to know how a CT works. A CT consists of an iron core, a primary winding, and a secondary winding. It operates on the principle of electromagnetic induction. When alternating current flows through the primary winding, it produces a magnetic field. This creates an alternating magnetic flux in the core. This changing flux cuts across the secondary winding, inducing a voltage and causing current to flow in the secondary, if a burden is connected. Now let's zoom in and see what's happening inside the CT's iron core during this process. The core contains tiny magnetic dipoles, like little magnets pointing in random directions. Let's first look at a normal condition, where the rated current flows through the primary. As the primary current flows through the positive half cycle, the magnetic field builds up and the dipoles begin aligning in the positive direction. But since the current isn't too large, not all dipoles get aligned, many still point in random directions. This means the magnetic flux continues to change throughout the positive half cycle, and the CT functions correctly. In the next half cycle, the current reverses direction. The magnetic field now flips, and the dipoles start aligning in the negative direction. Again, because there are enough unaligned dipoles left, the flux keeps changing throughout the negative half cycle, and the CT continues to track the current accurately. As long as the magnetic field stays within limits, the core does not saturate, and the CT behaves as expected. So what causes saturation? Let's now consider a fault occurs and a large symmetrical fault current starts flowing through the primary at point 1. At this moment, the magnetic field surges, and more dipoles align rapidly in the positive direction. Between points 1 and 2, the flux is changing, so the CT works as expected. The secondary current follows the primary current exactly, scaled by the CT ratio. However, before the positive half cycle ends, all the dipoles in the core get fully aligned. At point 2, the core becomes saturated. From this point on, although the primary current continues to flow, there is no change in flux. That means the induced voltage drops to 0, and the secondary current also drops to 0. Now, in the next half cycle, the primary current begins to reverse. At point 3, as the magnetic field flips direction, the dipoles start to align in the negative direction. This changing flux again allows voltage to be induced in the secondary, and secondary current flows again, until the dipoles become fully aligned in the negative direction at point 4. Once again, the core is saturated, and the secondary current drops to 0. This pattern continues. The CT saturates in both positive and negative cycles under symmetrical fault current. This behavior is also visualized using the well-known BH curve. When the curve flattens, it signals saturation. The core can't support further changes in flux. And here's the key idea. It's not the flux itself, but the change in magnetic flux that induces voltage in the secondary. So, when the flux stops changing, the CT can no longer generate the correct secondary current, even though the primary current is still flowing. So, to summarize, a CT saturates when all the internal magnetic dipoles are aligned. With no more dipoles left to shift direction, there's no change in magnetic flux, and therefore, no induced voltage. As a result, the CT can no longer produce the correct secondary current. That's the basic physics behind CT saturation. Now you understand what's really happening inside the CT when it saturates. If you found this video helpful, hit the like button and subscribe to WhatsApp with Power. Got a question or a topic you'd like covered? Drop it in the comments. We would love to hear from you. Thanks for watching, and see you in the next video.